Muchas gracias y buenas tardes. Mi nombre es Daniel Sistrunk y trabajo in Turner Construction. And it's an honor to be back here at the second Congress. And I want to say thank you to all the organizers of the Congress, and also a special thank you to Julian for inviting me back. Last year I had the opportunity to speak, and my focus at that time was on BIM integration in mega projects, a couple of which Julian mentioned. One was the Los Angeles Stadium, an entertainment district, which is the future home of the Rams and Chargers. The other project I shared about was a large aviation project at the Los Angeles International Airport. This year I'm switching gears a little bit, talking more generally about technology adoption as well as modular construction. So before we dive too far into the depths of the presentation, just wanted to outline the agenda. Start with an introduction, and then I'll dive into the technology adoption lifecycle. And I'm going to adapt that technology adoption lifecycle to some of the emergent industry trends in the AEC venue. Then I'll turn my attention to modular construction and share a few case studies, 3 of which are specific to projects that Turner is building, and then one is a new approach, which I'm calling optimized building units, which is actually one of our architectural colleagues in the California market. And I'll close with an application. Again, Daniel Sistrunk, Regional Logistics and VDC Manager in the Southwestern United States. I've got my QR code up there if you want to scan that and get a little contact information if you'd like to further our conversation. But first I'll start with a little bit about Turner Construction. Turner Construction as a company, we're headquartered in New York. We started there in the year 1902. But since that time, we've expanded our reach to work across the globe. Ever since 1965, we've been active in international markets, starting in China. We've been active here in Mexico and Latin America since 1981. 2015, we celebrated our 50-year anniversary, and now we're proud to say that we have a staff of over 1,400 people around the world building great projects. One of the focuses that we have as a company working internationally is projects that redefine the skylines. So one that you'll probably notice, I think we've seen some images so far today, is the Burj Khalifa, the tallest building for now in the world. We had the opportunity to serve as a construction manager on that project. And one other that I'm particularly proud about, if this is the right button, is number 59 there, which is the Wilshire Grand. And that's a project I personally had the opportunity to work on and actually shared a little bit about last year, and I'll describe more about the bathroom pods on that project momentarily. But the thing we're most proud about is that when we work internationally, it's not just the company from the United States going out and bringing a full staff with us. One of the key things that we do in those markets is actually partnering with the local community and the local professionals. So you can see the chart along the bottom. The vast majority of people that work with us on Turner International projects are local professionals. So that's one thing that we treasure, and one thing that we'd like to highlight as a way that we like to work with our local communities. So now diving into technology adoption life cycle. This was a life cycle that actually came to life first in the 1950s with an application in the agricultural sector. In the 1960s, it was adapted to innovation generally. And the version of it that I'm going to share today, it was actually then adapted further by Geoffrey Moore in his book Crossing the Chasm, which was released in the 1990s. And the major changes that Geoffrey Moore made at that time was that he applied it specifically to discontinuous innovations. And discontinuous innovations are those that require a change in the way that you operate when you're changing the tools or the methodologies that you apply to implementing a given process. And they also introduced this idea of the chasm. And I won't share the surprise just yet. But if you want to read more, I've got the information there. It's a great read. It's now in its 3rd edition, and it's been updated with references to Facebook and Mark Zuckerberg. So it's very current, very cool. So here's the curve that I've been promising. And one thing you'll probably notice is the backbone is a normal distribution. And therefore, beneath that curve kind of summarizes the probability of, in this case, a particular individual existing in a particular category. So in the original iteration of this curve, it was broken into the 5 categories that you see along the bottom. And what those categories are actually what they term psychographic categories. And psychographic is a combination of psychological and demographic. So these are folks with certain attributes that kind of group them together. They also have certain philosophies that unite them in each of these groups. So starting from the left to right, with the innovators. Between the innovators and early adopters, I would take the guess that the folks in this room exist in that group, but it's a small group. It's not the majority. It's not even the early majority. So it's a very select group of people, and innovators are those that pursue and appreciate technology for technology's sake. They're excited about new things that come out. They want to be the first to try them. They're willing to work through all the issues to prove out that technology. That group is separated from the early adopters in as much as early adopters are more established. They have access in their companies to R&D budgets, innovation budgets, and they're the people that take that technology and apply it to a business case. They see the value and they know how to apply it to prove that out and really make a difference to the bottom line of their businesses. That group is distinctly different from the early majority, which is most folks, as you can see there. Between the two, it makes up roughly 70% of the overall distribution. And those are the folks that understand the value of a new technology, but they want to see it proven. They don't want to mess through all of the bugs, support a company as they're developing a new approach. They want something that's tried and true, proven, that's going to add a benefit to their business immediately. And that's still separate than late majority. Late majority are those folks that are somewhat resistant to change, but they're willing to do it once the majority of the industry has gotten on board. And then finally, the laggards. These are the folks that oppose technology and change at all costs. And you might think that's a group that you can just ignore. But in reality, that group really provides the most valuable feedback about what their hesitation is to adopting particular technologies. So it's important to listen to them, even if they're not going to be the first to jump on the bandwagon. So this was the original iteration. And some exciting animations coming up. Boom, there you go. The chasm. So the chasm is that disconnect between the early adopters and the early majority. And Geoffrey Moore realized as he was adapting that model that chasm exists because people that are in the early majority typically will only accept references or suggestions from people that are in that same category. So that creates kind of a challenging situation because they only accept references from their own group, yet no one in that group is willing to try it out to prove out the value. So that's the reason we have the chasm. And looking at this landscape, I kind of try to take a summary of the emergent and existing technologies to see where they might fall along that curve. So this time I'll start from the right to the left with the laggards. So steel reinforced concrete might even be something that's comical to see up there. It's certainly not a new technology. It's very commonplace in our industry. But at one time, that wasn't the case. And in fact, the lore of Turner Construction goes that in the early 1900s, our company was the first to pioneer the use of steel reinforced concrete on our projects. In that case, a subway stairs project in New York City. Moving one to the left, the late majority, that's where I think I would put basic BIM. And by basic BIM, I'm really omitting the I in the BIM. This is visualization, it's 3D geometry, it's coordination. I think the majority of companies that have started on that journey have seen the value in that. They're applying it, they're implementing it successfully. That's not the case with true BIM. So now we're talking about the I, the information, and how we leverage that and exploit that. And this one probably, it may be questionable to some in the audience, and I would agree. There's certain applications and uses of the I, that true information in BIM that are very early on, but many of the commonplace things that we just heard about, like schedule visualization, site logistics planning, quantification, sustainability, some of those things are starting to move into that early majority category. And then if you go all the way to the far right, you look at things like artificial intelligence, automation, and robotics. And those are some of the things that are emergent. Folks come out and they have a great idea. They want to see what the application and the relevance to the industry is, and those are seeking their place in the industry. But I want to focus on those that are in the chasm. So starting from maybe the second one, virtual reality. I think that one's proven a lot of value in visualization, understanding of spaces, being able to do first-run studies. And it's on the cusp of making that leap into the early majority. And the one I want to focus on today is the one there at the bottom, modular construction. And I think I lump modular construction in the chasm generally, but as I'll show you on the next slide, there's a whole landscape of modular technologies that are at different places along this curve. Starting with the early majority, bathroom pods, and it doesn't need to be just a bathroom pod, but I'm talking about a distinct small piece of a building. Those have had a lot of project successes. There's been a lot of companies that have come up and pursued that kind of work. And it's moving more into that commonplace where people have seen the value, a lot of the kinks have been worked out, and it's being implemented successfully. One that's certainly in the chasm are building units. So now we're talking about a building that's comprised of individual modular building units. There's very little on-site stick-built construction. And this is a technology that is on the verge of making that leap to the main place. The next one's building sections. Now this is distinct from building units in as much as building sections are on projects that maybe weren't envisioned to be modular, but have certain logistical or constructability constraints that would require you to take a different angle and look at them in a different way. And it takes someone that has really a vision for how that project can be completed to make that leap and work through all the details and the bugs in making that a success. And then finally, all the way to the right, we now have this emergent technology of optimized building units. So one of the challenges with building units is that they have duplication of some of the construction in a building. They have duplicate walls between the units. They have duplicate floor and ceiling assemblies. An optimized building unit seeks to remove some of those constraints. We remove the wall and we join the two together to make a full assembly. So with that kind of background and landscape, I want to drop right into some of the case studies. First, we'll take a journey from right here at the Hard Rock Hotel. And we'll actually take the reverse trip that I took when I came here. We're flying all the way to downtown Los Angeles, California, landing right in the heart of downtown Los Angeles with the beautiful structure you see there, the Wilshire Grand. So as far as this project's stats are concerned, it's 73 floors overall. It has 36 floors of hotel, starting from level 31 to 66, so it doesn't start at ground level, it starts midway up the building. And in this case, we partnered with a pod manufacturer, SurePods. There were almost 700 prefabricated bathroom pods on the project, about 3 meters by 4 meter footprint, roughly. And there are 8 different configurations. And that's one of the key considerations when you're looking at modular, is how much variation, how much variability do you have in that product? Because that'll affect how economically feasible it is. It'll affect how much quality and repeatability you have in the production line. So looking at the details of the pod, you can see it's a fairly sizable bathroom. I think it's actually the size of my bedroom, interestingly enough. And the intent at the end of the day is that this blends seamlessly into the building. Once it's complete, you wouldn't know that it was ever prefabricated or built separately from the building itself. And one of the key elements to success in that was the depth to which the model was taken. So you can see an example of the model, the BIM that was developed here. It's fully detailed with all of the mechanical, electrical, plumbing utilities, points of connection for external connections, and all of the interior finish fully detailed. As far as coordination fabrication, of those units. One of the benefits of pods, apart from the schedule savings of on-site labor, was the fact that now you had this repeatable, predictable unit that you could coordinate to. So instead of having to deal with unique or intricate configurations, you had the ability to know exactly where the plumbing hookups were going to be, where the fire sprinkler would stub in to the unit, and it really facilitated a smooth coordination process. And then as far as fabrication, this facility that you see the interior of was located about a 4 to 5 hour drive north of Los Angeles in a city called Madera, California. And you can see that the production actually simulates what you might see in a manufacturing facility. There's rollers along the floor. These pods move from station to station, and a unique piece of that puzzle is put together in each of those stations. The complexities, though, don't stop at the production floor. Once you get these pods to site, now you're not dealing with raw materials and bundles of materials. You're dealing with a fully sized building within the building. And that required special rigging, which is the apparatus you see in the upper left-hand corner. These were all erected into place with the tower crane on the project. And it also required some out-of-sequence work on the floor. So you can kind of see peeking on the left side of the photo on the right, the current state. So it's basically roughed in with the fire sprinkler system, but nothing else is complete with the exception of this assembly that we called the T-wall. And that was a portion of the demising wall between the guest rooms and a portion of the corridor wall. And all that work had to be completed ahead of the time it normally would be scheduled in order to receive the pods. So kind of summarizing the lessons learned on that project, one was inspection. This was a process that was new to Los Angeles, and there was questions that arose about who bore the responsibility of inspecting the units. There were the hoisting considerations and the out-of-sequence work that had to be considered. So all of those are important factors to consider as you go in pursuing prefabricated bathroom pods. For our next project, we're going to go across the country from Los Angeles to New York to a project called 461 Dean Street. And this is a project you may have heard about that also goes by the name Atlantic Yards B2. And as we arrive, it's right next to the Barclays Center, home of the Brooklyn Nets, who I'm told is a good basketball team, maybe, I don't know. But nonetheless, you can see the tower here. It's a 34-story tower in a dense metropolitan area, approximately 34,000 square meters. And in this case, we also had a modular partner, Full Stack Modular. This project had even more even more modules than Wilshire Grand, had over 900 modules. And the unique part about this is these now weren't pieces and parts of the building. These were full sections of the building that were stacked on top of each other to form the actual enclosure and rooms within the building. This one also had the uniqueness that you saw in that previous image, that it's not a square building. It had a triangular shape, it had other configurations. And that resulted in the fact that it needed 65 different options for the modules, which added a fair amount of complexity. So again, the modules were fully detailed in using Revit in this case. And a typical floor plate is there in the upper right-hand corner. And you can see the different shapes and sizes and aspect ratios of the different components. All told, a typical floor had 36 individual modules that made up the floor. And you can see that the model was also used in the capacity of planning the production floor and the logistics, which is the layout you see there. And that layout you'll actually see replicated in the photo there in the bottom right-hand corner. But before we dive into that, the image on the left-hand side is actually the two pins represent the fabrication location for these modules, which was in the Brooklyn Navy Yards. It's about a 15 to 30-minute drive, depending on how bad traffic is, from the project site, which is the pin right on the bottom there. Similarly to the Wilshire Grand bathroom pods, this had a full-fledged production facility that was geared up. The distinct difference here is that the individual modules were not moved through the factory. They were built in place and then pulled out when they were ready for shipment. So each of these was kind of a mini project within a project, and all of the labor force and the materials came to the location of the individual modules to complete their work. Similarly to Wilshire Grand, since this did not have to be situated and kind of fit into an existing structure, it did have specialty rigging, but it didn't require a special platform. So you can see right off the truck, they maintained the protective wrapping, and they rigged these into place with also a tower crane. The steel you see there is the only structure that's not provided by the building modules themselves. So you, on this project as it was going up, you would see only vertical steel, which basically provide the lateral resistance for the structural system. But the platform that the workers are standing on is actually the top of the module right below it. And as you kind of cycle around, if you follow the arrows, you can see the status of completion as these modules are delivered. So the corridor is exposed, because since there's interconnecting piping connections that need to be made. But within the unit, everything is fully installed, fully complete, protected, of course, for shipping. But everything from the millwork to the plumbing fixtures, the flooring is all installed. And in fact, the image you kind of see wrapping around the small image on the right is the kit of parts, which are all the components that are needed to complete that assembly. So you can see how much of that module is complete before its arrival to site relative to the amount of work that needs to be done in the field. And ultimately, in the same way as Wilshire Grand, at the end of the day, the module looks just as if it was built traditionally in the field. The big challenges that they had on this project actually stemmed from tolerances. So with modular construction generally, you will need to specify tolerances that are in excess of industry standard. Specifically one, which is kind of the foundation literally for what these modules are landed on, is the concrete tolerances. In a Class A building, you might see an 1/8 inch and 10-foot floor flatness tolerance, maybe worst case, a 1/4 inch. This type of assembly requires precision on the order of a 1/16 of an inch or greater to ensure that you have full alignment all the way up the building of these modules stacking right on top of one another. So that's an important consideration as you're buying out the supporting trades that will facilitate this construction. Switching gears a little bit to a project that was not envisioned as modular, this is the Rockefeller University River Campus. It's just a quick hop, skip, and a jump right over the East River. Now we're going into Manhattan, ending up on the Upper East Side. And as we're diving into this, I want everyone to take a good look at the logistical constraints of this site. So on the west side of the site, you have the campus, the rest of the campus for Rockefeller University. You have a beautiful park. It's a research university, and they like to give the scientists a lot of quiet time and reflective areas that they can focus on exploring ideas for their research. So certainly no access to the project from that side. We don't want to do any disruption to the existing campus. To the north and south, you have existing buildings that span all the way out to the East River. And right between the campus and the river, you have a major thoroughfare, the FDR Drive, which is very active all throughout the day into the night. The project itself is not as tall as the others. It's just 3 floors, but it spans approximately 900 feet along the frontage of the river. It's 15,000 square meters, roughly. And in this case, there was no modular consultant. Based on the logistical constraints we just discussed, the Turner team came up with the idea of breaking this building into modules. So it was a traditionally designed structure. We identified logistical constraints, and we decided that we would pursue construction in a modular fashion to facilitate installation from the river itself. So what that manifested as is the fact that we actually broke it in that 900 feet into 19 individual modules. So this is a couple renderings of the campus as it will be at the end of the day. But after they decided to do that modular approach, they actually leveraged the input of some studies that they had received from from the engineering news record. So one of the project executives had seen an article about projects that had pursued this type of modular construction. He also looked at projects that had spanned that highway before and reached out to those folks, made the connections, and ultimately was able to work with the design team to revise the design to support this modular approach. So what you're seeing here is actually a wharf in New Jersey, and this is now not truck transit, this is barge transit down the river. And this is one of the 19 modules. So this area was actually created just for the purposes of this project, and the area was large enough that they could fabricate 10 of these modular sections at a time. So they had 19 overall. They'd work to complete 5. They'd start preparing those for shipment, move them out, and then they'd cycle through until they got all the way to the total of 19. The interesting thing here is that the construction of these sections is fairly traditional. They're using traditional equipment, they're using traditional materials. But the unique part about this is the fact that it is helping to enhance quality and safety. We're not working over an elevated road. We're not having to deal with overnight hours to do this construction. And overall, the building height's reduced as well, so you don't need things like a crane or other more expensive apparatuses to do much of the work. The transportation was the interesting part and the fun part. It's a beautiful image of sunset in New York City. So you can see one of those building modules loaded on a barge being pushed up the river by the tugboat. And the benefit to this was that it actually allowed them to go very quickly in the installation. So you see not much happening. That actually is a video that's playing. They're preparing, they're getting some of the foundation work in place, and then extremely quickly, within a 1-month duration, they're landing all 19 of those modules. So you can imagine how long that process would have taken to stick-built that construction if we had done it in a traditional way. To make matters worse, the restrictions on that FDR drive were such that you could only shut down one lane from 11:30 p.m. to 4:30 a.m., and you couldn't shut down the whole FDR drive until 12:30 a.m. So you had basically a window of 4 hours per night to work. And you can imagine how frustrating and challenging and dangerous that might be to do that volume and quantity of work in that narrow time span. But fortunately, with this approach, we were able to leverage that 4-hour shutdown and very efficiently install those modules. This is the process that they used to do that. One of the unique constraints is it wasn't just the 4-hour window, but you had to also match the 4-hour window with the slack tide. And the reason for that is as the tide comes in and out, you have currents in the river. And you can imagine the weight of these units being immense, that you can't have any movement or turbulence in the water that would affect the placement of those units from the crane. That crane's actually called a Chesapeake 1000, if you find yourself in the need for a maritime crane. But the team had to now not just look at weather patterns or other traditional things we might look at on the construction site. They then also had to look at tidal charts. So many months in advance, 9 months in advance, the team looked at those charts, mapped out when they had traffic constraints, shutdowns of the road, identified those windows, and ultimately decided that the summer break before school starts would be the ideal time to do it. They picked out 25 particular nights when we had this slack tide at the right time of night, and were able to land all 19 within that 25. They gave them a little buffer. Of course, BIM was a part of the execution of the work. You can see that they erected these, they verified the location and the coordination using the model. One thing that I do want to point out is it wasn't just the structure that they built off-site. Once they made the idea to go modular, they tried to think of everything that they could put in place before they brought the project to site. So they were able to place concrete on the 2 lower decks. They were able to run some of the fire sprinkler mains. They were able to install some of the lighting. and storm drains that came off the bottom, so they wouldn't have to access those from the street once they arrived. So they really tried to do that to the capacity and limits of the crane to make it a more efficient and smooth install on the project site. So that takes us now from kind of the current state, everything up to early adoption. And now I want to turn gears and look at the concept of optimized building units. So this project will take us back across the country from New York, from New York to Oakland, California. So we're going back to California. And actually it worked out great when I put this together because the image that you'll see is the substructure work that supports this modular optimized building unit construction. So all of the substructure work and the first level of podium were created traditionally using traditional means and methods on site. And as far as the project stats, this is a 6-story residential building. It's about 36,500 square meters, and it's comprised of 204 of these optimized building units. This is the only project here that's not a Turner project, and one of the reasons for that is that there's a company called Rad Urban, which is both the developer, the architect, the engineer, and the modular designer. So they're really taking full ownership of this process, looking at how they can benefit the progress and construction of these units all across the life cycle of the project. The unit itself kind of can show you what I was describing. They leave off one of the walls, they leave off the top of the pod, and the module. And the reason they do that is with the duplication in wall assemblies, you lose rentable square foot area of the building, which is very valuable from a development standpoint. And you also avoid the duplication of ceiling and floor assemblies, which minimizes the height of your building, and that has cost savings implications. At the end of the day, although it is a square rectangular building, it's certainly a nice looking building. It has architectural appeal, and its characteristics represent the community that it lives in. So this is a video that walks through the fabrication of these units. So you can see this is a very well organized, put together production floor. This is very similar to the Wilshire Grand bathroom pods, where you actually move the modules themselves through the different areas of fabrication. This is the framing station, for example. They have a drywall station, and then they rough in all of the utilities to this. So this gives them the opportunity to build on lessons learned, apply a lean construction methodology that takes them all the way to the wrapping and truck shipment of those modules to the site. And the fabrication facility is in the Central Valley of California, so it's also about a 2 to 3 hour truck trip to the site. These are a couple images once the modules arrive and are landed at the project site. The one on the left is looking up from ground level, and that's the only level of traditionally framed structure on the project. And one of the challenges they had going back to 461 Dean Street was with tolerances. So being that this steel structure was forming the platform for all of the modules above, they had to buy tolerances in excess of industry standards. So number one, it was a challenge to even find a contractor willing to accept that level of risk. And number two, they had to pay a cost premium for that. The other challenge they had with their methodology of making building units is that you can kind of see right here, after the modules are landed, they literally are exposed to the elements until the next module is landed on top or the roof is put on. This particular image is on the top level, so the roof will go over the top of this. And on the day I was there was actually rain in the forecast for the following day. So you can imagine the concern that they would have. Finished millwork, finished walls, finished flooring and everything installed in these units. So they were rushing at that time to maintain a weather-tight seal. This video now takes us into the erection process for these units. And similar to 461 Dean Street, you'll notice that there is vertical seismic bracing installed. and the only horizontal steel is really tying those seismic frames together, those braced frames. So you can see the modules. The one side is open. It's being moved into place, landed in place, and open to the environment at the current time. So that kind of shows you the custom rig that they have for the crane, how they set those, and how they tie them into those braced frame assemblies. So lastly, we'll take a trip back here to Guadalajara. And this is kind of the trip I took coming down here, landing back and exploring the city. And now we'll turn to application. So considering what we just explored on these case studies, I hope you have come to an appreciation of kind of how these different technologies fall in the technology adoption landscape. And I think one of the keys to continuing this progression to the right is for visionary owners, visionary companies to accept the risk, manage it, and actually push forward the envelope. I know on the building pods on Wilshire Grand, for example, it certainly wasn't a completely smooth process. But fortunately, we had a visionary project manager who understood that this trend was not just a fad, it was something that was going to continue on. And instead of running from that risk, has embraced it and has pushed forward to pioneer and pursue those types of projects in the future. All the way to the left on the innovator side, companies like Rad Urban are owning that full life cycle, and they're taking on that risk because they understand the value that it brings to the industry at large. So as we think about that, kind of pulling back a little bit, I want everyone to think, where am I at in my career? Where's my company? Where's my university along this curve? Are you an innovator within your company? Is your company pursuing innovative qualities? Or are you maybe in the late majority, in the laggards? I won't speculate on where I am or where you are, but I would hope and I would think that we're on the cutting edge. We're on the early side of that curve. And pulling out even further, looking at our countries. If you're early in your career, are there industry organizations? Are there groups that you could become a part of, or groups that you could start developing to push technologies and things you're passionate about to the next level? And as I close, I'm recalling a quote from Arthur O'Shaughnessy in his famous ode, "We are the dreamers of dreams." And I think it's our imperative as a group here that's focused on innovation to harness those dreams and take steps marching along that technology curve to turn those dreams into reality. Thank you.